Thank you, Duncan. So this is the second of the lectures on quantum circuits. And as yesterday, the slides should be live already on my webpage down at the bottom here. Now, what we talked about yesterday, what we talked about yesterday was sort of general setting of quantum circuits. So actually with a quantum circuits with a particular structure like this brickwork structure, which as I showed you had brought with it a notion of space-time locality. But we didn't talk about, we talked about sort of general things you might calculate to do with entanglement and correlation functions. And I showed you a formalism in particular for thinking about correlation functions near the light cone. But we didn't talk about any specific quantum circuits. And that's what we're going to talk about today. So I'm going to sort of pick out a couple of particular classes of circuits or circuit families which allow us to make some theoretical progress. So in other words, they have some extra structure which suggests some theoretical tool which allows us to make a calculation. So the two things which I'll focus on are random circuits. We sort of met this idea briefly yesterday. And then another class of circuits called dual unitary circuits. There are other kinds, other families of circuits which allow different kinds of analytical treatment to be developed. We heard one yesterday in Aditi's talk. Those were Clifford circuits. You can also have things which can be mapped to free fermions, free bosons, and so on. Okay, so just a quick reminder of one of the things I told you about yesterday, which was this notion of operator spreading. If we look at the evolution in the Heisenberg picture of an initially localized operator, say a Z operator at some particular site. And I said that just in general, you can expand that evolved operator in terms of products of local Pauli operators. When I say Pauli operators, I mean including the identity operator at each site with some set of coefficients, which I'm calling C here. And those coefficients will evolve in time, and that describes the spreading, the time evolution of the operator. And then, one other thing to bear in mind is that because the Heisenberg evolution conserves the operator norm, that implies a normalization condition on the squares of these coefficients. Okay, so what I told you last time was that inside that very complicated set of coefficients, there's some useful information. So for example, the correlation functions that we talked about yesterday can be thought of as just one particular component. So if I start, these coefficients start off at time 0 with only one non-zero component corresponding to having a single Z operator localized at one site and identity operators everywhere else. And then if at time t, I pick out a similar component, but with a Z operator at some site k, then that corresponds to just the correlation function, the ZZ correlation function at these two sites, J and K, and at time separation T. But that's only one part of this whole family of coefficients which describe the spreading of this operator. And you might ask, what about the rest? And can we characterize it in some way? And one of the ways that operator spreading can be characterized, which captures situations even when the correlations vanish, is something called the out of time order correlation function. I'm always tempted to say out of time order. Yes, it is the right order. So it's defined like this. So it's a 4 operator quantity, and the out of time order part reflects the fact that we go time 0, time t, time 0, time 2. So it's if you're familiar with time ordered correlation functions which appear in many body physics or quantum field theory, this is where it gets its name. I'll define it in this lecture as at the top there. It's often defined as the square of the commutator of the operators at time 0 and time t, and then their expectation value. Those two things are related using z squared equal 1 just in this way. So just as a warning, you may see some papers where the OTOC is defined differently. Okay, so why is this something which tells us about operator spreading sort of beyond what's just in the correlation functions? So let's look at this representation in terms of the commutator to begin with. So based on what I told you last time, if we're at we have this notion of a light cone in these circuits. So at short times, the two spatially separated operators at sites J and K are going to commute with each other. and therefore this OTOC at short times will be equal to 1. If you want to know what it does more generally, you can substitute in this expansion of the time-evolved operator in terms of these coefficients C, and obviously you have to substitute it in twice because Zj at time t appears twice. And when you just write this out, you get an expression for the OTOC in terms of these coefficients, but in terms of the squares of these coefficients. So if the operator at initially localized at site J spreads until it includes some non-identity operators at site K, then the OTOC will begin to deviate from 1. Okay, so if you don't have any, if at short times the only operators at site K are the identity operators, that corresponds to the first Kronecker delta there. Then using the normalization condition, we get an OTOC of 1. After non-identity operators start appearing at site K, the OTOC begins to deviate from 1. So the time at which the OTOC starts deviating from 1 for a given spatial separation defines a characteristic velocity, and that has a rather colorful name, the butterfly velocity. It's after the butterfly effect, and it's denoted by VB, so that defines this quantity VB. And the other sort of nice feature of this quantity is it depends on the square of these coefficients, and so it tends to survive averaging if we consider, as we will later on in this lecture, families of random circuits. And if you sort of remember, when we first introduced this idea of averaging in the last lecture, we were thinking about a correlation function. I was taking this gate, which was just came from the exchange Hamiltonian, and by averaging over the exchange coupling J, you tended to average out the correlations, and that was because the C's have signs which tend to average out when you do this averaging over random circuits, and that won't happen with the OTOC, so you'll get some non-zero signal even when the correlation functions vanish due to averaging. Okay, so this was measured experimentally, I think for the first time by Google in 2021 in this circuit setting using the Sycamore quantum computer. And the thing that I want to highlight about this, so what these color-coded plots here are showing you the spreading of the OTOC from an initial site as time progresses from left to right. And there are actually two experiments which are represented here. One of them, so all of these experiments involve averaging over single qubit gates, which we're going to talk about in the first half of this lecture. But they are averaging over a core 2-qubit gate, which is either a I-swap gate in the top row here, or the square root of an I-swap gate. I realized that I told you what a swap gate was last time, but I didn't tell you what an I-swap gate was. I-swap is just, it has a I where the 0 and 1 gets switched, it has an I. Okay, but it's you can think of it as being similar to the swap case. And then the lower case is the square root of this I-swap gate. And so if you look at the OTOC, which is plotted here, as time progresses, so there's a number of cycles in the circuit, what you can see is a spreading, which displays this characteristic butterfly velocity in both cases, in fact. But the difference between the top case and the bottom case is that in the square root of I-swap case, the spreading is spreads out. So you don't have it in the top case, you have a sharp front which spreads. In the bottom case, you have some spreading, but so you have a front which spreads, but it also gets wider. It also spreads diffusively. Okay, and what we'll explain why this happens in the course of this lecture. Yeah. Yeah, so it is a 2D, exactly. So relative to what I've been talking about so far, where we just had space and time, this is actually 2D, and then time is a third direction. So yeah, as we take image to image, weird time is progressing. Well, I mean, this is, I mean, it's not so easy to see in the color coding, but it's easier to see on the right-hand panels here. So this spreading, this front here is measured at different places. So these different traces corresponded to measuring the OTOC at different separations as time goes by. So it's not, we're not sitting at a, we're not looking at traces at different times. We're looking at a trace with respect to time at different places. Yeah. Yes. Yes. Is not, but yeah, we'll come to it. Yeah. Okay, so one thing before we go on, which is really just a parenthetical remark, is that the OTOC and this notion of operator spreading is actually only one way of quantifying the evolution of a local operator. So there's another notion which is operator entanglement. And so what, you know, the simple-minded way of talking about this is to say that operator spreading is really, you know, how big are the strings of operators which appear in this expansion. But you can also ask a question about how many non-zero coefficients are there. So you could imagine just having one big fat operator and no other contributions. It would have a large amount of operator spreading, but it wouldn't have operator entanglement. And the way in which operator entanglement is formalized is extremely closely related to the way that just entanglement of quantum states, of state vectors is formalized. Namely, you do a Schmidt decomposition of operators. So if you have an operator which acts on a system which is composed of two subsystems A and B, then you can use exactly the same notion of a singular value decomposition to write that operator as a sum of operators, tensor product of operators acting on A and B separately, together with some coefficients which are called the operator Schmidt coefficients. So it's really just the same idea. These ANs and BNs are orthonormal now with respect to the Hilbert-Schmidt inner product, but other than that, it's exactly the same idea. And if you want the very simplest version, you know, the simplest idea, you remember when we talked about state entanglement, I said the Bell state was the very simplest idea, gave you the very simplest example of a Schmidt decomposition. The very simplest case that you can think about for the operator case is the decomposition of a swap operator. And we saw last time that you can write the swap operator in terms of XX, YY, ZZ, and 11. And this is exactly the Schmidt operator decomposition of the swap operator with all the Schmidt coefficients equal. Okay, so you can then define entanglement measures, the entanglement entropies, and so on in exactly the same way for these operators, and this is another way of characterizing the dynamics of a local operator. Okay, so now I want to talk in a bit more detail about this idea of random circuits, and we met this idea last time when I introduced this family of exchange gates parameterized by some theta, and we averaged over some distribution of theta. S here is just the swap operator. So now we're going to consider something which has got even more randomness in it. So last time I gave you this decomposition of a 2-qubit gate in terms of some core 2-qubit operator V, together with unitaries which sit on the 2 legs, incoming legs, and 2 unitaries which sit on the 2 outgoing legs. And what we're going to do is to consider averaging over circuits by averaging over those single site unitaries which sit on the legs, by keeping the core V fixed. Okay, so Simon was asking me yesterday, I think I'm paraphrasing more or less, like why the hell do you guys care about this kind of problem? So I think, you know, one answer would be like the kind of the marketing answer is that, you know, if you have a family of random gates, they don't have any symmetries. So if we average our results over a whole family of random gates, the results should be generic. And that comes with a heavy, in some sense, as theorists like to say, which means, you know, it's a kind of aspiration more than anything else. But the real reason maybe is that when we average, as we'll see, when you average over circuits, you often can introduce a tractable, even classical description of what's going on, which you wouldn't have for a single instance. So what we're going to do is choose these gates to be independent, identically distributed. You could have other situations. You could, for example, choose the gates in one row randomly at each site in space, and then repeat those gates in time. That would correspond to a kind of random Floquet evolution. Amos has worked on this problem quite a lot. If you want to know more about the random circuits in particular, there's a very nice review by Matthew Fisher and friends, which has just been published. Okay, so we're going to look at this OTOC in the case of these random circuits. And the first idea is that the OTOC can be extracted from the tensor product of two copies of the evolving operator. And the way to see that is, if I want to evaluate the OTOC as defined in the top line from that tensor product, I just need to insert my ZK at time 0 twice, once between the two operators, and if you like, once wrapped around the two operators in order to evaluate the OTOC. So if I can evolve this tensor product of the two copies, then I'll be able to extract the OTOC. Now, as we evolve these two copies, the important thing is that they're evolving in the presence of the same random gates. So when we average over the random gates, only certain components of this tensor product are going to survive. And since we're averaging over gates independently on each site, the components which survive are going to correspond to invariants that we can make locally, invariants that we can make from the two copies. Okay, and since we're talking about qubits, and since just SU2 that we're averaging over is just identified with the rotations, it's particularly simple because we can just think about what scalar operators we can make from two copies at each site. And if you think for just a minute, probably less, you'll realize there are really only two options. One is you can take two copies of the identity operator, or you can take two copies of XX plus YY plus ZZ. And those are the two invariants that you can make at a site. In many papers, you'll actually see a different basis used. You'll see identity times identity and the swap operator. So bear in mind when I say swap here, I'm talking about swapping the two copies. We're not swapping two qubits on different sites, but swapping the two copies that we're making. This is another basis, another pair of invariants. The advantage of this choice is it generalizes very nicely to multiple copies because the general invariance, if you've got many copies, corresponds to just permuting between the copies. The two copies, there are just two permutations, the identity and the swap permutation, which is what these correspond to. Okay, but I'll stick with the other basis that I wrote down. It's easy to move between the two. Okay, so what we're going to do is use that basis of invariance to expand the average of the two copies. So I'll define this O2 as the average of these two copies of our evolving operator. And the two basis states I'll call them 0 and 1, which corresponds to 1, 1, and this XX, YY plus ZZ. And then we introduce a basis, so that's just a one site. Those are the invariants of one site, and then we introduce a basis in which we'll expand this averaged O2 just by tensoring those invariants together across all the sites. And so the general averaged O2 is written as a superposition of those with some coefficients P, which are evolving in time. So if I knew how these coefficients were evolving in time, then I can extract the OTOC from there. Okay, so then the next thing is to find out how P evolves in time. And the way in which we do that is we imagine starting from our current averaged O2, and we apply gates, and then we take the average. So applying gates means we have to apply the gates to both copies. So we apply U dagger U on either side for one copy, and likewise for the other copy, like this. And as I said before, we're going to take our U's to have this core 2-qubit operation, and then 2 unitaries sitting on the legs. I don't need to take two incoming unitaries and two outgoing unitaries, because when I stack them together to make a brickwork pattern, the unitaries at the columns will combine with the unitaries for the rows, if you see what I mean, or the unitary at the top will combine with the bottom of the next unitary, and so you only need to average over two. Once we do the averaging, all the non-invariant components of this thing will vanish, and the invariant components obviously don't depend on uj and uj plus 1, and then we can extract the coefficients at time t plus 1 just using the orthogonality of these two invariants, 0 and 1. Okay, so at that point it's sort of reduced to a problem of algebra. But the general structure of what comes out of that is this: your coefficients at time t plus 1 written in terms of your coefficients at time t by applying some matrix which acts on the indices corresponding to site j and j plus 1. And that the actual form of that matrix, omega, depends on the precise form of this core 2-qubit operator, which forms the core operation in the circuit. And obviously, at that point, you just have to work out what omega is. But there's something you can say about the form of omega, which comes from the fact that the operator norm is conserved. Because the average, if we take that conserved norm and just average it, then we can express it as just the sum over all of these coefficients. So what that tells us is whatever this omega matrix is, it has the way it updates the coefficients p is in such a way that the sum over all the coefficients is conserved. So that means that the sum over a row, so a sum over the Sj, Sk of this matrix omega is equal to 1. So hopefully that rings a bell. If in addition these matrix elements were non-negative, that means we'd be dealing with a Markov process. You can think of the coefficients p as a probability distribution, which is conserved in time. Normalization is conserved in time. There's a gap in this argument, of course, which is that I didn't give you a reason why they're non-negative. They are, if you calculate them. There's actually a third basis, which I won't go into, where you can actually explicitly understand why they have to be positive too. But the nice thing is we get a Markov process out of this. And as I said, it depends on this core gate V. So at that point, you have to work it out. So if you look in the supplementary material, the very extensive supplementary material for this Google experiment, you'll actually find a calculation of this matrix omega for the sycamore gate in terms of some parameter theta, which is pi over 2 for the I swap case and pi over 4 for the square root of I swap. But the important thing, it's not really that. The important thing is that we've got a Markov transition matrix here. You can see as you sum over a row, you get 1. Okay, so this is a fantastic simplification because we've taken this many-body quantum problem, we've focused on a particular observable, the OTOC, and we've averaged, and we've turned it from a quantum many-body problem into a classical stochastic problem. And this is a big win. This idea is actually sort of, sufficiently useful that it's been rediscovered repeatedly over the years. The earliest use of this idea that I can find is this paper by Oliveira, Dalston, and Plenio from 2007, which was concerned with not OTOC, because it hadn't really been invented at that point, but the dynamics of the average purity. I'm actually making this point because if you look in the supplementary material to the Google paper, there are no references at all to any prior work. So it wasn't invented. It wasn't invented by them, but obviously it's the setting they were working with is their own. So the way in which the purity works, by the way, is you can extract. Remember last time I told you the purity was the trace of the square of the reduced density matrix, and so in the same way that you can extract the OTOC from the tensor product of two copies of an evolving operator, you can likewise extract the purity from the tensor product of two copies of the density matrix. Okay, so what does this Markov process actually look like? If you look at this transition matrix, it describes two kinds of process, really. So remember, we've got these two kinds of states at each site. The 0 corresponds to the identity operator. for the two copies. And the transitions that can happen are with probability A, 1, 0 on two neighboring sites can switch to be 0, 1. And with probability B, I can go from 1, 0 or 0, 1 to 1, 1. And with probability B over 3, I can go from 1, 1 back to 1, 0 or 0, 1. So note that the 0 state is inert in some sense, or it's like a vacuum. There are no transitions to or from the state 0, 0. And this makes sense because that state is the identity for the two copies. And so it doesn't evolve under the unitary time evolution at all. Okay, so what does that mean? The nice thing, of course, with the fact we're dealing with Markov processes, we can actually just look at it. This idea has a name. I mean, any kind of simple sort of process like that must have been studied before, and this one is called the Fredrickson-Anderson model. So this is what it looks like if you start. This simulation starts from zeros everywhere apart from a single isolated 1 in the middle. And then because of these transition rules here, that 1 tends to spread out into a region which contains a mixture of zeros and ones. In fact, the stationary state has got 3/4 1 and 1/4 0. I have a feeling this simulation is actually 50-50 because it just looks nicer. But in this case, in our case, it's 3/4 1/4. Okay, and of course, this is representing in the average sense what the operator spreading looks like, right? So if we start from a localized operator, it spreads out, and the fact that it's I was about to say the fact that it's stochastic is a reflection of the fact that the circuits are random, and that's a slight fudge, if you like, because when you sample from the Markov process, it's not really the same thing as the averaging over the gates that we've done. It's sort of tempting to think of it in this way. So this was I plotted this obviously just to have a nice picture in the two-dimensional case, which is sort of the kind of thing which is going on in this Google experiment. If we take a space-time picture, so 1 + 1 dimensional picture, then you can see that you get this front which is propagating at a finite velocity, although of course that velocity will fluctuate. And so we see this idea of a butterfly velocity emerging. Yeah. Yes. Yeah. Yes. Yes. Yeah. Yeah. That's right. That's right. Yeah. So, yeah, exactly. It's almost impossible not to conflate the two things, though, isn't it? Yes. Okay, and so the other thing, which again shows up in the average, so it's okay, is this notion of broadening, and so if you depending on what you choose for your core, you will have different probabilities A and B in this Markov process, and so that captures what they look at in the experiment when you go from the I-swap case to the square root of I-swap case. So what happens in the square root of I-swap case is in some sense the generic situation, which is that the butterfly velocity is less than 1, is less than the maximal value. In other words, moving from one site to the next in one click, and accompanying that, there's a broadening of the front as time progresses. In the I-swap case on the left, the speed, the butterfly velocity is actually maximal, equal to 1. And as a result of that, there is no broadening at all because everything moves as fast as it possibly can, and there's no possibility of spreading beyond the light cone. So this, it captures the qualitative features of the experiment very nicely. If you ask about the broadening of that front, it's known that it was studied, I think, beginning with this paper here. That it's known that in the 1 + 1 dimensional case, that front broadens diffusively, so like the square root of t. The two-dimensional case is more interesting. It obeys the Kara-Priggi-Zhang dynamics appropriate to a growing interface because it really is a growing interface. And so that would mean that if the Google experiment could be done at sufficient scale, then I guess you would see this KPZ broadening in the front. So yeah, one thing I just want to emphasize about this is you reduce the dynamics of the average OTOC to a classical something you can simulate classically. The appearance of a sort of a Markov process is a little bit surprising, but there is there is interesting quantum physics to be had in these experiments. One way you can think about that is in terms of the fluctuations of the OTOC, so how it varies from shot to shot, and that would be captured by averaging the tensor product of 4 copies. And again, if you look at this, the theoretical supplement to the Google paper, they actually go through this exercise, which is probably pretty unedifying exercise of working out the dynamics of this thing. And the upshot is that you don't get a nice Markov process out of it. You actually get your updates to these the coefficients that describe this average have signs in them. You have a sign problem, and therefore you wouldn't have an efficient way of simulating the fluctuations of this quantity. We found the same problem in a problem we worked on a few years ago, looking at the average OTOC in models which have number conservation. We found a similar issue. Okay, good. So the second kind of circuit that I want to talk about is with particular structure that makes it soluble is something that's now called the dual unitary circuits. And so to motivate this, let me remind you about this example of flow K evolution that I gave you last time, namely the kicked Ising model, which is composed of this Ising part and a transverse field, which appears at regular kicks. And one striking discovery that was made a few years back was that there's a special point, which is now called the self-dual point, where the magnitude of J, the Ising coupling, and the magnitude of the transverse field are equal, both equal to pi/4. And Bruno Bettini and his co-authors found that they could calculate this. They could calculate the entanglement entropy in this situation, and found that it grew at a maximal rate before saturating. So you have this very sharp growth and ramp structure. And this is exactly the same kind of structure that I showed you last time. It's a very simple model of swap gates acting on Bell pairs, starting from an initial state of Bell pairs. And so although this kind of behavior, this kind of broad structure is familiar from other settings like this, beginning with this Calabrese-Cardi work, the fact that this happens at maximal rate and then saturates abruptly is unusual. Okay. And the other unusual thing about this was although it happens at this fine-tuned point where J and B are equal to pi/4, it happens for any values of the longitudinal field and for any product state if you start an initial product state in the Z basis, in the computational basis. Okay, so this is kind of striking behavior, and actually all of these Renier entropies, which I told you about last time, turn out to have exactly the same behavior. And if you remember, they were defined in terms of the power sums of the eigenvalues of the reduced density matrix. And so the fact they all do exactly the same thing is telling you that all of the eigenvalues of the reduced density matrix are equal, and all the non-zero eigenvalues are equal, and they're all equal to this number here. If you take this and plug it into one of the Renier entropies, you get this ramp in the corresponding entanglement entropy and then leveling off. Okay, so if you want to frame this in terms of thermalization, you can say that after a number of steps which is proportional to the size of the system, the reduced density matrix of the system has become equal to 1, and you can think of that as the system has thermalized at infinite temperature. And so all expectation values take on their infinite temperature value at that point. So you have a very kind of sharp characterization of thermalization and abrupt characterization of thermalization. Okay, so it was sort of a curiosity about this system that made Sarang and I ask ourselves this question about what happens what's special about the circuit that you make when you phrase the quantizing model as a circuit. And I told you how to do that last time by breaking by making a gate which has got a little Ising interaction followed by a kick on each side followed by an Ising interaction. These are the explicit forms of those operators here. And so the case of the self-dual point corresponds to J and B equal to pi over 4. And what we found was that at this point, this gate has an additional property which is called dual unitarity. And so just to refer back to this graphical notation that I introduced in the first lecture. Remember, I had this diagrammatic language for blue unitaries on the left there and red U daggers, their conjugates on the right. And the condition for unitarity of these gates took the form of contracting on both sites in the vertical direction and being left with a Kronecker delta on each side. So that's how the condition of unitarity looks. And then I introduced this folded picture where you fold the gates on top of each other, where the condition looks even simpler. You now contract among the two indices which make up each leg at the bottom or at the top, and you're left with a Kronecker delta in the same way. Okay, so that's generic for unitary gates. And so the very simple idea is just to apply the same criterion, but just in the horizontal direction. So instead of contracting the two bottom or the two top indices, you contract the two left or the two right indices, and then impose the condition on these gates that you get Kronecker deltas in exactly the same way. Okay, so it's an additional constraint on the form of the gates. So let's see what that does. Now, I showed you last time how the reduced density matrix looks for a general unitary circuit. And we're going to look at how that calculation is modified when you additionally impose the condition of dual unitarity. So we'll start with this block of 8 sites and 4 layers. And remember that when I use the condition of unitarity, I can start removing those gates at the top, which have been contracted over. And if I do that as best I can using just the condition of unitarity, I'm left with this wedge here. And along the bottom, I've got these bell pairs, which act as my initial state. So now, so at that point, with unitary gates, I'm stuck at this point. I can't do anything else. But I do now have the ability to use this dual unitary condition, because if you look at sort of the extreme left and the extreme right, you can see that accounting for this bell pair, which forms the initial state, I can use this dual unitary condition to start removing things from either side. So from here, and then I can actually keep going. You can see every time I move, I've still got 2 things contracted on the left, and I can keep removing these gates, and the same over here, and eventually I end up with this structure where I've used systematically both the unitary and the dual unitary conditions. And so then it's a question of interpreting this thing. Actually, I could go further. I could switch back to using the unitary condition, actually take away all the gates, or the other way of interpreting this picture here is to say that the purple triangle here represents a unitary transformation acting on a density matrix or an operator, which is just identity times 8 times, corresponding to this bottom part of the triangle. And of course, if I act on such an operator with a unitary transformation, I'm going to get the identity back. So this shows me that the reduced density matrix is just proportional to the identity, so it's infinite temperature. If you go through the same exercise with a shallower circuit, which has just got 2 layers here, then apply unitarity in the same way. We get this shallower wedge, and then you start applying the dual unitary condition. We end up with this, so that's as far as you can go. And how should you interpret this picture? This is a unitary transformation which acts on an operator, an initial operator, if you like, which is composed of the identity. Those are the 2 blobs on the left, identity for the two blobs on the right, but in the middle, we've still got two of these Bell pairs. And so we have just a projection operator, two projection operators onto those four sites at the bottom, corresponding to those that Bell pair, those two Bell pairs in the initial state. So this then is the circuit which remains is a unitary transformation which acts on this initial state, and therefore is something non-trivial. You can't actually, it's not easy to say in general what that is, but you can say what its eigenvalues are, because obviously unitary transformation doesn't change the eigenvalues of the initial state. So what you've got in the general case is a unitary, once you've used dual unitarity as much as you can, you have a unitary transformation which acts on this initial density matrix where you've got t minus 1. So t is the depth here. You've got t minus 1 copies of the identity, or actually 1/2, because that's just normalization. And then you've got some remaining, in general, you'll have some Bell pairs remaining in the middle, which give you eigenvalue 1. And you see what the effect of going deeper is just to reduce the number of Bell pairs which are left over. So then if you work out the eigenvalues of this reduced density matrix, which is unaffected by the subsequent unitary transformation, they're just the set of eigenvalues that we found before, which describes the rapid growth of the entanglement and then saturation of all the entanglement entropies. So this shows you that just the property of dual unitarity and the initial condition, which I put in here, which seems rather special, these Bell pairs, but we'll come back to that, are enough to tell you that entanglement growth is maximal. And there's a paper last year which showed that the converse is also true. If you impose maximum entanglement growth, then that tells you that your gates are dual unitary. Okay, so it's a alternative characterization, if you like, a more physical characterization of this class of circuits. So how special is this condition that we've imposed? As I told you last time, the 4x4 unitary gates are 16-dimensional. It's somewhat surprisingly, this putting on this extra condition of dual unitarity only loses you 2 parameters, so you still have a 14-dimensional space. It includes this Klick-Ising model at particular values of the couplings, as I've told you. And although we've been able to obtain exact results, we're not talking about integrable models, which are normally much more fine-tuned. If we had taken the self-dual Klick-Ising model, for example, at 0 magnetic field, is integrable, but you can all that I've told you applies also at finite longitudinal field. So it's just that they have kind of just enough structure to make certain calculations tractable. Now, I sort of cheated you at one point, which was to do with the initial conditions. So let me remind you, when we talked about this analysis here, we started from this initial state, which consisted of Bell pairs, which obviously a rather special choice. The original paper by Bettini, Cos, and Prozin studied the self-dual Klick-Ising model starting from an initial state, which was a product state in the computational basis. So it wasn't a Bell pair state. So why did it work? And that's because the Klick-Ising model actually has an additional property which allows you to get going removing the gates, which is just written here, okay, in the unfolded picture. So there's some additional tweak in the Klick-Ising model, which makes these kind of rather natural initial states solvable as well. Obviously the natural question is then, is this just a kind of peculiarity of the initial states? And some more recent work has looked at that. So this paper by Pirelli et al. In 2020 looked at what they called solvable initial states, which actually had a matrix product form where basically exactly the same thing happens. You basically create a matrix product state which has some special structure which allows you to start using dual unitarity to remove the gates. So those are still solvable in the same way, but they again special. In fact, they're more or less all generalizations of this Bell paired state. Then more recently, these authors this year looked at more general initial conditions, and the result there is that although for a general initial condition you don't get this maximal growth initially, then asymptotically you do, and this connects back to this result by Zhao and Harrow. Okay, so what else can we say about things we might be interested in for these dual unitary circuits? One of the other early results here was to do with correlation functions. So last time I introduced this graphical representation for the correlation functions. On the left was like how it starts off. On the right is what happens after you've used unitarity to remove as many of the gates as possible. And apart from those pictures, there's a kind of, I told you there's a sort of simple physical picture to do with a light cone, which tells you where the correlations are non-zero, only inside the light cone. And so if you know, and that, I told you that was just a consequence of unitarity. So if you now impose unitarity in the spatial direction instead of in the temporal direction, as well as in the temporal direction, that tells you that correlations also vanish in outside of a spatial light cone. So in other words, a sideways light cone. And if they vanish outside of this light cone and outside of this light cone, there's only one place they can't vanish, which is on the light cone. And so this is a feature. So the calculation that I outlined for you last time, which evaluated the correlation functions just along a light cone, although that looks like a rather special point, it turns out in the dual unitary case, that's the only place there are non-zero correlations, and therefore you have a complete characterization of the correlations in the dual unitary family. And that can actually, you can have all sorts of different behaviors, even within that family. You can have ergodic behavior, you can have oscillations and so on, all just by tuning the parameters within that family. So this was actually measured last year, this experiment by Continuum, where they actually studied the self-dual kick-tizing model and actually were able to extract correlation functions. And I just grabbed this picture. The details of how they did the experiment is somewhat complicated. The title of the paper has holographic in it, so it's enough to scare me a bit. But anyway, you can see the comparison between the theory and the experiment is pretty good. There's another picture which I didn't include of the non-self-dual case where you can see the correlations are not concentrated on the light cone in this way. Okay, good. So this is this is a nice kind of benchmark, the sort of thing that people who are building quantum computers like to go after. So the other applications of dual unitarity, they sort of continue to grow sort of in the last few years. And I've just listed just a few on here, and this was just a kind of personal selection I made this morning, but there are many others by now. So just to connect back to the Google experiment, so we looked in, Peter Kleiss and I looked in 2020 at the OTOC in the dual unitary case. So in that case, you don't have to do this averaging to be able to calculate the OTOC. The dual unitarity is enough to do it. And you find, it wouldn't be too surprising that the butterfly velocity is equal to 1 in the dual unitary case. So that connects with the Google experiment because this ISWAP gate, or rather gates which are obtained by dressing this ISWAP with unitaries, are all dual unitaries, and therefore it's consistent with this maximal butterfly velocity you see in that case. You don't have to be playing with this for too long before you get the idea to go to 3 dimensions. There's no by which I mean 2 + 1 dimensions. I showed you how this worked when you had unitarity in the time direction and one spatial direction. Well, why not just make unitarity in another spatial direction? And so you can do that. I mean, the dynamics is somewhat more. You end up with correlations which only vanish again along. A non-zero along a line. In that case, you've, if you like, got 3 separate light cones to think about, and their intersection gives you lines. But there are other so-called tri-unitary circuits which were in the plane but had a hexagonal symmetry explored in the second paper. Wenwei and collaborators had this very nice paper just at the end of last year about doing measurement-based computation in a 1D architecture using dual unitaries, using the kick-tizing model. Also at the end of last year, there's a very nice paper from Grace Summers to do with dual unitaries, which are also Clifford circuits. And there you have a kind of cellular automaton, as we heard yesterday in Arijit's talk, but it's cellular automata which has a sort of maximal velocity light cone, and they discuss some applications to codes. And there was a rather intriguing paper as well, also last year, which was to do with the computational power of dual unitaries, and was pointing out that something interesting that happens there as a function of depth of the circuits in 1 and 2D, that you get a transition in the hardness of simulating these dual unitaries, different from the general random unitary case. And probably there are many more and many more to come, but that's all I wanted to tell you about, and hopefully that gives you a flavor of the kind of calculations and the kind of ways that people have been approaching unitary circuits. Theorists have been approaching these kind of unitary circuits over the last few years. Okay, thank you.
So you mentioned, can you summarize the results that what self-dual gets you more than the dual unitary?
Oh, well, I mean, self-dual is just, that's coming from the Ising, language from the Ising model.
Yes, I understand, but there are results that are true in self-dual, but you couldn't show in the generally in dual unitary.
Well, I don't, but I don't think there is a general notion of self-duality in the dual. It's overloading the word dual, I think. I don't know if there is a general notion of self-duality for dual unitaries. I think you can generalize the Ising case to higher spins, to Q-trips and so on, and then you can look at particular kinds of dual unitary circuits which have self-dual properties for these higher Q-dit cases, but it's not a general feature of dual unitarity. Probably we should change the name to something like space-time duality or something like this.
Oh, sorry, I didn't mean to say that self-dual or dual unitary are self-dual.
Yeah.
I'm just asking.
Does it get you anything?
It gets you more results, right? Like the initial state.
Oh, the initials, yes.
There should be other results that also.
Oh, I see. You mean which depend upon that initial state, which depend upon that kickdizing property that I called.
For instance.
Okay, sorry. Yes. Are there other? I'd have to think about it. I think they're mostly basically come down to this initial. The fact that you can get going with an initial condition, I think it mostly comes down to the same thing. There may be something else, but.
Thanks.
Are there any? Oh, yep. If one considers a randomized version of the dual unitary, I mean the description you had of this classical Markov process, that still goes through, or
yes, yeah, it does. It just it's just a particular case. What does it do? I think a 0-1 always turns into a 1-1.
I see.
It shoots off.
I see. Yeah.
Just fills up basically on the average.
And the higher order averages.
I don't know. Actually, that's a very good question. So you were saying if I were to specialize the dual unitary average, would I end up with something tractable? That's a good question. I mean, well, I'm cheating by referring to this result here, but presumably that must break down because they're saying that eventually when they are computationally hard in some way. So but it's a question of where it breaks down.
Yeah. Hey, one question. If you change the measures, is there some way of, at least in the cases where these are related to Hamiltonians and so on, like kick rotors, to go to a point where you don't flow all the way to infinite temperatures? Like you get some finite temperature quantum states?
You mean as the stationary states? I don't know of any. I mean, you could do things like work with gates which have conserved quantities, so then you go to infinite temperature, but within a particular sector, right? So I don't think so, because I mean the point is it's effectively like just driving something with a white noise or something. Maybe if you've got measurements or something like that, some additional coupling of quantum system in, maybe you can do something.
Do you have any intuition as to why this swap gate is integral, but the square root is not?
Well, I mean, saying why things are not integrable is kind of like, that's the expectation, right? Well, do you mean this one here? I mean, well, I mean, swap gate by itself is very simple. I-swap gate adds an extra phase, so I would say that doesn't change much because you can just keep track of the extra phase. So I think it sort of maps onto sort of in that case it maps onto a kind of a simple classical dynamics, and if you need to, you can keep track of the extra phase as well. There may be people have, I didn't actually put the reference, but there was a nice paper last year by Balash-Posgai which talked about things with automata. So in other words, so dual unitary automata. So these are dual unitaries which also permutation matrices. You can think of them as being like classical cellular automata. And then there they looked at things which satisfy Yang-Baxter. So there is a more formal answer there. But yeah, but they're rather considered as integrable models. They're even rather special because they have this classical picture. I don't know whether Sarang has any thoughts on that.
Sorry, so I'm still confused about the Google experiment. Is it like looking at operator spreading on a 2D lattice,
Yeah.
or it's so? I mean, why don't we see something like I would expect like a circle growing?
Well, because they can only measure particular points. The protocol only allows them to. So the way they do it is by evolving with some U, applying an operator, and then evolving with the U dagger. So they actually they evolve, and then they extract the full OTOC, which is a UU dagger from some probability. So you can't measure the entire profile, I don't think. I mean, maybe if they worked harder, they could do it. But
Okay.
I guess it's all to do with which qubits they can couple in.
So you're looking at a kind of a cut.
Yeah, so they can only just sample the OTOC a few locations from the original site and look at how that depends on time. So they're just trying to pick up the spreading of the front with this butterfly velocity.
Questions? Okay, then let's thank Austen again.
Thank you.